Topics for today are physical versus chemical reactions, evidence of a chemical change, chemical equations. For a physical change, now we saw this back in chapter 1, but it's good to review it anyway. In physical change, the state, shape, or size of the material changes. Here you see a person, they're boiling some water on the stove for, looks like for pasta. So what is the physical change going on here? Well, that's water, liquid water becoming steam, as you can see down here in this diagram. The identity and the composition of the substance don't change. Now, liquid water is H2O and so is steam. So chemically they're exactly the same. When a chemical change is different, these substances react together to form substances with different properties. And in this example we have a silver fork, and you can see the silver down here, Ag. And it's tarnishing, and the tarnishing of silver is a reaction between silver and sulfur to form silver sulfide. So silver sulfide looks different than silver. It's black almost. And the way you reverse the process to get the black out is not to rub it off, which you could do, but you'd also be losing silver, but to chemically take the sulfur out of there. You see evidence of a chemical change here would be the color change. And we see color changes, number one, formation of a gas. Now this doesn't mean like heating the water to the boiling point. That's different. Kind of expect that to happen. But if you put two things together and suddenly a gas is produced, that's what we mean here. That would indicate a chemical change. Formation of a solid, a precipitate. Now some of you may know what a precipitate is and some might not, but you're going to see an example today. And also we'll be doing a lot of precipitate reactions in chapter 4. And the fourth thing, heat is produced or is absorbed. Sometimes things get cold as well as getting hot. Now, although that can be evidence of a physical change as well as a chemical change, usually for a chemical change you need two of these things. Here are some examples. Let's check out the chemical changes. The rusting of a nail is definitely a color change there, and plus the rust breaks off from the nail and it falls apart. It's one reason why iron isn't too good for using as nails outside. Bleaching a stain, we had a color change there. Burning a log, a lot of heat produced. Tarnishing silver, we already went over. Fermenting grapes, that's when yeast feed on the sugar on the grapes. Souring of milk, well, sour milk tastes terrible. It's all lumpy and it has a lousy odor to it. So we could have included change of odor as well as evidence of a chemical change. Here's some examples. Nylon being drawn from the boundary of two layers of reactants. Nylon is actually produced from cellulose, which is wood. Evidence formation of a solid. Here we have hydrogen gas and oxygen gas being produced as water decomposes. So if you put a 9-volt battery into a glass of water, maybe throw a little salt in with it, this reaction will take place. If you look closely at the diagram, you notice that looks like there's more gas coming from this electrode than from that one. So that's when we see the 2-to-1 ratio between the gases. Here's when you might use this winter. You use a warm pack to produce heat to keep your feet warm or your hands warm. Here's a chemical reaction where we start off with some cobalt nitrate solution, which is red, and then we add some hydrochloric acid to it in the middle one, and you see the red becomes blue. Now here's a formation of a precipitate. Adding two solutions, one sodium dichromate, that's this one up here in this beaker, and lead nitrate solution, which is clear down in this beaker here. And the instant they come together, we get a precipitate form. A precipitate is a solid, and one of the properties of that solid is that it doesn't dissolve in water. So we made something new here. Whereas the other two, sodium dichromate and lead nitrate, are both soluble in water. Here's another example. We add calcium metal to a beaker of water, and what happened? Instantly we get bubbles of gas produced. We've all seen this one already, burning the old gas from the Bunsen burner. Example of a chemical change, heat's produced. Alright, now we're going to be writing chemical equations to summarize these chemical reactions. Chemical equation shows the reactants and the products. And we're going to balance in the equations, and that's really the focus of the rest of this session. Now when we write a chemical equation, we're going to be using some of these symbols. We're going to put a plus sign between the reactants and also between the products if we have more than one. We're going to put an arrow between the reactants and the products instead of putting an equal sign. The arrow tells us which way we're going, what we started with and what we ended with. We always start with reactants and we always end with products. Sometimes there can be heat or light produced. If that's the case, we put a triangle over the arrow. Now you're going to see this, sometimes you won't see it happening, but sometimes you will. And we can also indicate the phase that a substance is in by putting SLG or AQ. And AQ means a solution in water. First thing we want to do is review the meaning of a formula. Here's an example. This is iron 2 nitrate. If you take it apart, you see that we have 1 iron, 2 nitrogen, and 6 oxygen. If I put a 3 out in front of that formula, how does it affect everything? Well, that 3, you notice it's written as large as the capital F. That 3 is going to multiply the entire formula. You get 3 iron, 3 times 2, 6 nitrogen, 3 times 2 times 3, 18 oxygen. And that 3 is called a coefficient. And when we balance equations, we're going to be writing coefficients. So you've got to remember that a coefficient will multiply the entire formula and any subscripts in it. So let's check out a chemical reaction. We'll look at the equation. So here we're burning some carbon. This could just be charcoal. And the chemical equation we have is CS, that's carbon solid, plus oxygen gas yields CO2 gas. Now let's check out the atoms and see if it's already balanced. We have 1 carbon on each side. We have 2 oxygens on each side. This equation is already balanced. Nothing for us to do. Mostly the equations won't be balanced though. So we're going to go through how to balance some equations, and I'm going to give you some at the end to do. Here's a reaction between zinc and hydrochloric acid. Now zinc readily reacts with hydrochloric acid, producing hydrogen gas. Now we obviously get another product. But the product, we don't see that because it dissolves in the solution that's there. Here's a word equation describing what we have. So our 2 reactants are zinc and hydrochloric acid. We read the arrow as yields, and our 2 products are hydrogen gases and chloride. Now in order to write an equation, the first thing to do is replace all the names with their formulas. And you got to be careful, because when you look at something like zinc chloride, don't assume it's just ZnCl. The formulas are all based on the charges, just like we saw in chapter 2. And hydrogen gas is diatomic. So here is our equation. So we're going to balance this now. So here's the equation again. And I break down the atoms, see what I have. There's 1 zinc on each side, so the zinc is all set. There's, the hydrogen is not balanced, and the chlorine is not balanced. So I'm going to balance for the hydrogen. And I'm going to do that by putting a 2 in front of the HCl. So when I put a 2 here, it's going to multiply both the hydrogen and the chlorine. See my result now. So 2 hydrogen here, 2 chlorine there. This equation is all balanced. It was pretty easy. All right, let's try another one. Glass is silicon dioxide. And we can etch the glass by using hydrofluoric acid, HF. So these are our 2 reactants. And silicon tetrafluoride and water are 2 products. So here is our unbalanced equation. So let's balance this one. Alright, break it all down now. After a while you don't have to break it down, but in the beginning it might be good, so you go slow with it. So let's see what we have. We have 1 silicon on each side. The hydrogen, that's not balanced. We see that. The oxygen isn't balanced, neither is the fluorine. Well, I'm going to balance, I think, for the fluorine first. I could have balanced for any of the others, it wouldn't matter. I'm going to get the same result at the end. So to balance for the fluorine, I need 4 on the left to balance the 4 on the right. So we have to put a 4 in front of the HF. Remember, the only place you can put a number is outside a formula, never inside the formula. Now I'm going to balance for the hydrogen. Now you notice that I'm starting with 4 hydrogen now on the left, and there's only 2 on the right. So I need 4 on the right as well, so I put a 2 in front of the water. Now when I check out and see what I have, 1 silicon, that's balanced. 4 hydrogen, that's balanced. 2 oxygen, 4, I'm all done. Now what are my coefficients when I'm finished? I'm going to include the number 1 when I read the coefficients. That way I know where all the numbers really belong. So my 4 coefficients would be 1, 4, 1, 2. Here's a reaction between potassium metal, stored in oil to keep it away from water, and we have a beaker of water. So what happens when I drop the metal into the water? Pretty violent reaction. It's hard to tell what's really going on by just looking at it. But chemically, this is what's happening. The potassium, when it reacts with water, produces hydrogen gas and potassium hydroxide. The hydrogen gas is flammable, and because this reaction produces a lot of heat, the hydrogen gas is instantly ignited. It's not what my eyes see, but that's really what's going on. Let's balance off this equation. Now when I break it down, this is what it looks like. One potassium on each side. Hydrogen isn't balanced. One oxygen. You notice that there are 2 hydrogens on the left, but there's a total of 3 hydrogens. Could add these together on the right. Odd number, even number. Anything I put in front of water will affect the hydrogen. I'm going to want to stay away from that one. So how can I lower the number of hydrogens from 3 to 2 on the side? Well, I'm going to do that by putting a 1/2 in front of the H2. Well, 1/2 of an H2 would mean just 1 hydrogen. Let's see the result. 1 hydrogen here, 1 here, balances off that. Now, I'm not supposed to leave a fraction when I'm done balancing. In order to get rid of this, I'd multiply all my coefficients, which right now are 1, 1, 1/2, and 1. Multiply them all by 2. So therefore, my final answer is 2, 2, 1, 2. Okay, now here's another one where you could try a fraction. Why don't you try to balance this one on your own, and then come back and see the solution. So pause the slide at this point. Okay, let's go through it now. I break it down. Notice the hydrogens are all set, but the oxygens are not. I want to balance for the oxygen, so I'm going to use a 1/2 on the right. This will lower the number of oxygens on the right. So you get 1/2 O2. Now, 2 hydrogens and 2 oxygens. I'm all set. But I have to get rid of that 1/2, so I'm going to multiply everything by 2, and there's my final answer. We can check that out. So what are my coefficients when I'm done? 2, 2, 1. And you must say the 1. Okay, now here's the Bunsen burner operating, and we're burning our gas, and then our reactants are methane and oxygen, and our products over here are CO2 and water, and here's our equation. Let's balance this one off. Again, I'm going to break it down so that we can see all the different atoms. There's 1 carbon on each side, 4 hydrogens here, only 2 over there, a lot of oxygen everywhere. We balance an equation like this. We want to balance for the easiest ones first. And oxygen is not the easy one because it's in both products. So I'm going to leave the oxygen to the end. So I'm going to balance for hydrogen. I can balance for carbon. So to balance for the hydrogen, I need 2 on the right. So I'm going to multiply the water by 2. And that's what I would have. So you notice 4 hydrogen, 4 hydrogen. Now that has increased the oxygen from 1 up to 2. So the total amount of oxygen is 4 on the right now. So I just have to multiply the O2 by 2, and I'm all done. My answer then, 1, 2, 1, 2. Here's another one you might want to try first on your own, and then come back to see the solution. Okay, so here I go. I'm going to balance for the iron by multiplying Fe by 2. You notice that the iron is all set, but the oxygen is not. I have an even number on the left and an odd number on the right. So here I'm going to use the idea of smallest common number. The smallest common number between 3 and 2 is 6. So I want to get 6 oxygen on each side. In order to do that, I have to put a 3 in front of the O2 because this will mean 6, and a 2 over here. Now that did upset my iron, but I can then go back and balance for the iron, and now I'm all done. Here's another one to try. Break this one all down. You can see, okay, we have the carbon isn't all set. Carbon is 2 and 1. Nothing is balanced. Again, we want to let the oxygen go to the end. So I'm going to balance first for the carbon. So to balance for the carbon, I put a 2 in front of the CO2. And this multiplies the oxygen as well. Okay, I'll come back to that later. Now I'm going to balance for the hydrogen. So I have 6 on the left, I need 6 on the right, so that means a 3 in front of the water. Okay. Alright, so now I'm ready for the oxygen. Ooh, total amount of oxygen here, 7. 4 and 3, and only 2 over here. I'm going to have to use the fraction 7/2 so that this will actually mean 7 oxygens. So here it is up here now. So the meaning of 7/2 of O2 is 7 oxygens, and that balances that off. But remember now, we can't leave a fraction in an equation, so we want to get rid of this 2 in the denominator. So I'm going to have to multiply all my coefficients by 2. Then my final answer becomes 2, 7, 4, and 6. Now here's what I want you to see with polyatomic ions. We don't have to break the polyatomic ion apart. In this case it's nitrate. You notice it's on both sides. We can keep it together and treat it as one thing. So when I break it down, I'm keeping the nitrate together. This makes balancing a lot simpler. So I'm going to balance for the nitrate. So I need 3 of them on the left to balance off the 3 on the right. Putting a 3 there will do that. This is what I have so far. Okay, so you notice that this 3 changed the nitrogen. The chlorine isn't balanced either. I can do either one. Let's see what happens. I'm going to balance for the sodium. When I put a 3 in front of the NaCl, that also balances the chlorine. So I took an equation that looked difficult in the beginning, and I saw by keeping those polyatomic ions together, it really wasn't so difficult at all. So my final answer then is 3, 1, 3, 1. Now here are some for you to try. So write these down on a piece of paper, try them, pause where we are, and then come back and you can continue on and see the answers. Okay, here are the answers for A and B. Now here I'm including the ones just so you remember that's what they mean, but normally we never write the number 1 unless we need to, and we don't here. So just by saying N2, the meaning is 1 and 2. So technically though, if you were asked what are the coefficients, you would say 3, 1, 1. You wouldn't just say 3. Now here are 3 more for you to try, so that's a total of 5. So let's see if you get 100 on all these now. So copy these 3 out on a piece of paper, try to balance them, then come back and check the answers. Okay, here we go. The answer for the first one, 2, 3, 4, 3. Letter B, 2, 3, 3, 1. And for letter C, 2, 3, 1, 3. Okay, and that is the end of the show.